And hello again, welcome to another stream here on Freaky Physics. And yes, we're continuing today with more review for IBDP Physics as the exams are again on Tuesday. Well, Tuesday here on my time zone. So of course, I wish everyone good luck with the exam soon, and I'm gonna go into the lesson soon as well. Um, for that though, let me change my camera settings. Figure right there. Again, I look more like myself. There we go. Oops, it's too high. Yeah, that's good enough. All right, good. And let's go into the classroom. Well, I'm in the classroom already, so just waiting. Yep. All right, I learned from yesterday's lesson that I should have I should have another screen looking just at the stream. So yeah, I'm looking every so often at my other screen here. The other screen's my phone. I didn't bring a new one yet. I'll probably get one soon once I have the funds for it. All right, I'm also getting ready. Okay, so we had a few more questions last time about special relativity again. I kind of purposely left those out for the end because I think that needs to be practiced slowly so we can get it properly. Okay, so I didn't want to go through the whole thing immediately. All right, just open all the questions and I have the board ready. I think I will share my board with the student for now. All right, and speaking of which, hello Gita, good evening, a good day. And
Good day.
all right,
How's it going?
doing good. You?
Great.
All right. Okay. Uh. Okay. So we'll have you sent anything new yet, or are you doing that
It's
now?
loading. The Wi-Fi's a bit slow today,
Okay.
so
No
I'm trying
worries.
to.
No worries about that. Um. All right then. So I'm just gonna get ready to go on the stream again. Okay.
Mhm.
Guess what happened while you're setting up and everything. Guess what happened yesterday during the stream?
Oh,
I did not
uh,
put the board into the stream as I was talking. So I was just talking the whole time.
oh no. Oh no.
Nah, that's fine though. Alright, so okay, I see the problems you've sent over.
Oh,
Let's
I
open.
didn't realize there's so many.
Yeah, that's fine. It's not that many, I guess. 5, 6, 7, 8, 9. Alright, so let's start again. Alright, so let's start with this question, the one about the probe going around the Earth. Okay. Now, okay, so in this case, your space probe, the mass is 95 kilograms and it's designed to land on the surface of an asteroid where the gravitational field strength is given. It's quite tiny, 2.7 times 10 to the minus 3 meters per second squared. The radius of the asteroid is given as 230 kilometers. So how do you calculate the mass of the asteroid here?
For this one, I found the mass. It was mostly the second question that I
All
wanted to
right, so
go
let's go
over.
to the second question then. Uh, the probe is carried to the asteroid on board a spacecraft. I'm looking for the second part of that. Hold on. Where'd it go?
Hmm.
No, that's not it. That's not it either. But it's oh, okay, I think it's this one. It's a continuation here, the one about the constant force exerted by the rocket
Yeah.
engine. All right, good. Let's take a look at this question. So there's the second part. Okay, so this time around, the force is given. It's exerted by the rocket engine. It's 12 newtons. So determine the time for which the rocket must fire to reduce the speed of the probe from 0.64 meters per second to 0 and state the answer to an appropriate number of sig figs. Okay, since the easiest way for, actually no, since it said constant force, right? uh okay, just state the number to an appropriate number of, okay, determine the time for which it, all right, I'm thinking again, this is without the marking scheme, so we're not sure exactly to what level we need to go through, but I'm gonna go all the way through, okay, with the how to solve this. So in this case, in part, I just gotta ask, in part one, does, or at least before this, does the rocket go down, or the probe, does it go down into the asteroid, or does it stay on that circular path? I'm
Um,
gonna say it's,
I,
or is it gonna just drop? That's the thing. Okay.
the only part, all the question is in the screenshot. There's
Okay.
nothing I left.
Nothing left. Okay. So part one doesn't really have any information, right? About this.
Yeah.
Okay. Um. Okay. So in this case, what's the time about the rocket to reduce the speed of the probe from 0.6 to 0? Okay. So in this case,
Oh, sorry.
okay. Go ahead.
So question C is, as the probe approaches the surface of the asteroid, a
Mm-hmm.
rocket engine is fired to slow its descent.
Okay. There we go.
Um,
All right. So to slow its descent, so that basically means, let's draw this first on the side. This basically means this is already near the surface of the asteroid, right? That makes it easier. That actually makes it a bit easier. So because of this, this is the probe, and it's gonna go here, and we know that at this point it's going at 0.64 meters per second, and here it's gonna be 0 meters per second when it touches down, right? Okay, that makes a whole lot of sense now. Now, the idea here now is that we have to draw the free body diagram on this thing, again, on the probe. In this case, we have two forces. It's the force from the rocket, and then the weight. Okay? In this case, what else do we know? We know that, we know this is near the surface, so we know here that G is constant, more or less. Okay? G is constant, and we know that the resultant force, the rocket's force is 12 newtons. Okay, do we know the mass of the probe?
95.
95 kilograms. So the mass of the probe is 95 kilograms, so this weight here, this is gonna be equal to 95 G, but we're not gonna use the G of Earth. We're gonna use the G of the asteroid. It is given that it's 2.7 times 10 to the minus 3. Okay, so let's just write that here. We're not solving yet. It's 95 times 2.7 times 10 to the minus 3. So from here, what's the resultant force? The sum of forces, or the resultant force, should be equal to MA, right? Okay, one more thing. Is there anything else given, like the height it must go through? No, it doesn't. But we need that height, actually. Okay, let's just assume that we don't know the height. So let's just say that the height it travels here is h. Okay? Alright, so in this case, this is one way for you to approach this. Another possible way for you to approach this and would be to think energy. Okay, so at the beginning, the energy here is gravitational potential energy. That's gonna be so if we do energy, we do mgh. That's plus the kinetic energy. So 1/2 mv squared, right? That's the beginning. Then at the end, we know that the 1/2 mv squared is going to be 0 because it's going to slow down. And also that the mgh is also going to be 0. But this is going to be the work done by the rocket, which is going to be, the work done by the rocket is going to be 12 times h. Okay? We still need to find, no, hold on. Actually, do we need height? I still think we need height. Because what's the question here again? We are looking for the time. So, okay, since we're looking for the time, this will not be feasible. We have to use force equals ma. Then we find the acceleration here. That will be equal to the force, which is going to be 12 minus, what's that number? 95 times 2.7. So let's just do that here. 95 times 2.7 exponent negative 3. That 0.225. So 0.252565, and that's gonna give us an acceleration of, or deceleration rather, of how much? So minus 12, 11.74. So the acceleration equals 11.74 meters per second downwards. Okay. All right. So that's the acceleration. And it's gonna be constant because we are assuming that it's near the surface of the planet. Okay. So what's next? From here, we need to know the time. So here we just use kinematic equations again. So which kinematic equation is good to use here? And again, we can use that because this is constant, right? The best kinematic equation here is one that doesn't have height, it just has time. So we can just use v equals u plus at. That's the fastest way. So our v is 0, our u is what was it again? 0.64, right?
But can
0.64.
we just use A is equal to change in V over time?
You can do that as well because actually that's a equals change in v over time. These two are equivalent.
Oh,
Okay. Uh, so anyway, yeah. So you can use that. Either way, we'll get to this solution. Okay. So we get this. Then that's gonna be our acceleration is gonna be negative. So let's just note it here. Down. Upwards rather. Right. Okay. So that's upwards. So that's not negative. However, the v going down is negative here. It's going down. So that's negative here plus 11.74 t. And just solve t from there. So 0.64 divided by 11.74 times 0.64 negative. That's gonna give us a time that is a very short time of 0.054 seconds. Okay.
okay.
All right. Okay. So state your answer to an appropriate number of sig figs. Our answer must have 3 because we're given 3 sig figs here. Okay.
Okay.
All right. So that's the answer there. Questions?
It's very clear.
All right.
Thank you.
Good. Let's move on to the next bit. Which one is?
I think this question is finished, but could we do the most recent 2 pictures? I just want to clarify something
All right.
with
Two most recent pictures. That would be the
the
ones I
graphs.
just sent. Yeah.
Yeah.
All right. So the graphs. Flux linkage and time. All right. So let's do that and do that. Okay. Um. Copy this. Okay. Let's do the first image because that's from the book, right?
Yeah.
Okay. But
Um,
the idea here, let's go into the formula that relates the two, magnetic flux linkage and induced EMF. Okay. While waiting for the image to load, the equation is the induced EMF is equal to the change, well, let's put negative here, negative change in the magnetic flux linkage per unit time. Okay, so um let's just label that again, change in flux linkage. Yeah, in fact we should have an n here to be more complete. All right, so let's just put the n here. The whole n phi is the flux linkage. Okay, what is n here though? N is the number of turns. Okay, now let's go back to this image and let's see what that means. First of all, let's take a look at the first graph, magnetic flux linkage over time, right? So in the first section here, there's a change in magnetic flux linkage, right? Change in phi here. In this section here, there is no change in phi, right? And similarly here on this last bit, there is a change in phi. So this is a positive change. Let's put the signs. This is a negative change, right? So far, clear?
yeah.
Okay, so we put this idea into the formula. Remember that the EMF, the induced EMF, has a negative sign in the equation. So basically, this positive change in the flux linkage leads to a negative EMF. Negative EMF. There. Okay, that's why it's negative here. Okay, and if you look here, this is a straight line. In this case, the change in the straight line is a constant change. Okay, so because the change is constant, what do we know about it now? If the change is constant, then the induced EMF itself is also gonna be constant. It's gonna be a straight line if you graph that. Similarly here on this part here, the change is negative and constant, so the induced EMF would also be constant and positive. So that's why we have this here. And the last bit here, there is no change in the flux linkage. So since there's no change, the EMF is zero. Okay.
And where did the minus in the equation come from?
It comes from Lenz's law. Meaning,
Okay.
the EMF that's induced will always oppose the change that's causing it. Okay.
Okay.
All right. So let's go back to this. We've done this together, if I recall right. We've done this problem together, but it's a little bit weird simply because this time you have curves in the flux, right?
Yeah.
Okay, so if the flux linkage is curved, then it is changing, but the change is not constant. The change in this particular case, while we're waiting for the image to load, the change is increasing. It starts from a low value and then it goes to a high value. How do we know that it's an increasing change in the first part? Okay, what you can do here is you can just look at the gradients, okay, or the slopes of the tangent. So okay, let's zoom in a little bit so I can show you what I mean. So if we zoom in like that, I'm gonna draw a tangent here. There's a tangent line going here and a tangent line going here, right? So what's happening here? You start from a low change, a low change here, right? And this is a large change because of the slopes being small and large respectively, right? So in other words, if you start absolutely from here, your gradient here is 0 at the very beginning. Okay, so you start again from a 0 value for the flux linkage, and then it slowly goes up. And if this were parabolic, and I'm gonna assume it is, if this were a parabolic curve, this means this is increasing the increase the change, let's just say it like that, the change is increasing linearly. Okay, linearly. So what's gonna happen if you graph this EMF now? So for the first part, the EMF is going to also increase, but it starts from a zero value to its maximum value. That's why it's like that here. Okay,
But sorry,
go
in
ahead.
the when we had the graphic
Mm-hmm.
of the ring going into the coil,
Mm-hmm.
we said that because it's passing the lines which are not exactly consistently like increasing, that's why
Mm-hmm.
it's curved. But in the book, I'm pretty sure it's the same example, except they draw a straight line and then they say that the EMF is constant. So when the coil is entering when the ring is entering the coils,
Mm-hmm.
is the flux
Yeah.
consistently changing or inconsistently?
It really depends on the context, but realistically, it's gonna be the one we talked about. That it's gonna start off from a zero value, and then it's gonna start increasing slowly, and then it's gonna change. It's gonna abruptly change. Okay.
And
Uh,
in what case is it constant?
okay. What case would be a constant change? The best way for you to be constant, to get a constant change in the magnetic field, is if let's draw the solenoid here again, right? Okay. If I draw the solenoid here, and I'm instead of a battery, I have here a power supply. Okay, an adjustable power supply, and then the ring is here. What for now for a constant uh delta B, right? For a constant delta B over delta T, what could happen is this power supply is slowly is increasing the current linearly. Okay, linearly, linearly, and then the ring doesn't move and the solenoid doesn't move, so these do not move. Okay, so the ring in this case will experience an increasing yeah, it will go for an increasing amount of yeah, the increase would be constant as well. Okay, so
Even though
this
it's
is
not
one
moving.
case. Yeah, because what's gonna happen as the current increases, the magnetic field from the solenoid also increases.
Huh. Okay.
Okay, all right, and in those cases, where in that case, because the current basically dictates is directly proportional to the magnetic field produced. So if you increase the current linearly, the magnetic field increases linearly as well.
Okay.
Okay. Um. All right. So of course, the last bit here is here. Here in the middle, because the magnetic flux is not changing inside the solenoid, the EMF is zero in the ring. Okay.
Yeah. Sorry.
Go ahead.
For this example that you gave, the EMF is increasing or the flux is increasing?
The flux is increasing. The flux is increasing, and then it stays constant, and then it decreases. It's it stays constant inside the solenoid.
Mm, I mean when the ring is not moving.
Oh, you mean for this one, right? So
Yeah.
the magnetic field will increase if the ring isn't moving, and it's gonna be linear. It's gonna increase linearly, again because the current is increasing linearly.
And the EMF?
The EMF would then also be increasing linearly. So if we're gonna graph this, this is the phi, right? It's just gonna do that. Okay. So what is this gonna be? This so in this case, if we're gonna do the EMF rather, if we're gonna do the EMF here with time, because it's increasing linearly, the EMF is constant.
Okay.
Okay. All right. Anything else?
Um, I understand. So it just depends on the context, but usually we would say that it would curve,
Mm-hmm.
but in this case,
Mm-hmm.
it could be constant, the flux.
Right. Okay. I Oh, okay. I just saw one question you sent over. I wanna check the physics guide. Yeah,
Okay. Which one is it?
the capacitor problem in the physics guide. You sent over a capacitor
Mm,
problem. I don't.
right.
I tried manually looking for it, and I tried searching for it on the guide. It's not there. Capacitors are not in the exam, apparently.
Huh. Uh,
I'm gonna.
I think it's
I'm. We'll
23 paper.
we'll just do it either way, just in case, right? Because I think your teacher might have discussed it with you anyway, right?
Uh,
All right,
maybe.
maybe, hopefully. But again, I'm looking everywhere, both the data booklet and the physics guide, and from memory as well. I don't see any capacitor problems or capacitor related
Okay.
stuff. So we can do that later, I guess, just in case it gets covered. Okay, so we'll skip it for now.
Okay.
All
And
right,
just one question.
go ahead.
Regarding the contents of the exam,
Mm-hmm.
um, do we have the inverse Lorentz transformation formulas in the exam?
That's a good question. I am
I
gonna
saw them in the book.
I'm going to say probably not. Okay,
Okay.
because all you have to do is, if it's gonna be reversed, you're just gonna do the Lorentz transformation either way anyway, right?
Yeah, but how do we reverse them?
Okay, I'm gonna have to think of an example for that, or maybe you can show me the problem in the book later on. Yeah.
Okay.
All right. Okay, which problem do we do now? Um. Okay, let's do this problem about, okay, this multiple choice problem first, because this is still kind of related to magnetic fields, right? And currents.
Mhm.
All right, so the next problem I want to go through is this one. So you have a wire carrying a current I placed in this region of a uniform magnetic field B as shown. Okay, so the question is, which way is the direction of the force and what's the magnitude of the force? Okay. Do you have an answer to this before?
I thought A.
A. Um, Hold on. I'm gonna do this real quick. B is out of the page. Current is already that way. It should be A. It is A.
But how do we know the magnitude?
Okay. Um all right, I'm just gonna say that that's the idea here now is, remember, all three must be perpendicular. The magnitude, the current, the magnetic field, and the force, right? Now, let's take a look at the B and the I first. They are in fact perpendicular to each other, right?
Yeah.
Okay. So B is already perpendicular to I, or you can think of this as B is perpendicular to L, right? Okay, but more importantly, the I is the thing here. So this already tells us that the force is perpendicular to both B and I. Okay, and when that happens, when they're both perpendicular, then that means, this also means that with this particular case, this also means that the force is maximized. That's it, maximized. Okay, now
And
now I want to show you, I think the confusion stems from the fact that there's this angle here, let's just say theta, like that, right? That will still give you the maximum force because, again, the B and the I are perpendicular to each other. I'm gonna draw an example of what it looks like for the B and the I to not be perpendicular. Okay, so okay, this I could draw like so. The B is gonna be like that. Okay, and then in this case, I'm gonna draw two current carrying conductors. One, and we'll label them 1 and 2. Okay, so that's 1, and this is 2. Okay, you can see here that for 1, the angle is 90 degrees, right? So perpendicular. But in this case, what is the angle between the magnetic field and B here? That's our theta here. And in this case, the theta is less than 90 degrees. It's not perpendicular. So this is where you would have a smaller. So in this case, you still have the force equals BIL. Okay. And in here, the force is equal to BIL sine 90 degrees. Okay.
In the field from the current, the magnetic field, does it interfere with the other field?
If sorry, say that again. I didn't quite get the question.
If we do the right-hand rule, we know
Uh-huh.
that the L wire has a field. So would
Hmm.
it interfere with B and have another direction?
Uh, that's actually the reason why there's motion, because the fields interact with each other. But that's a longer way to actually describe it. The faster way to do it is just to use the left hand rule. But basically, the left hand rule is more of a mnemonic rather than an actual physics thing. Okay, the physics part of it is exactly what you said. Those two magnetic fields, the external one from the field or from the region, and then the magnetic field from the wire, they interact, and the way they interact is the wire will move.
The wire?
This wire, this
Um,
L here, yeah. So again, the complete reason is this wire here has a magnetic field, and there's another magnetic field. Those magnetic fields interact. It causes the wire to move. Similarly here, yeah.
how does it move? Like
Uh,
in what way?
Now, the movement will is best described by the left hand rule. But
Oh,
okay,
the force.
yeah, because of the force. Now here in 2, what happens here? Because if you think about it this way, because of that angle, um, remember that magnetic fields and currents only interact when they're perpendicular to each other. So basically, we're only looking for a portion of the current or a portion of the magnetic field that would be perpendicular to the other one. And that's going to make it smaller. That perpendicular bit is always smaller than the whole magnetic field. Okay? Clear?
Yeah.
All right. So that's why the answer here is A. All right. I think that's clear. Uh, which one is good after this? Total charge on the plates, time left. I'm just curious what this is. Oh, okay. Let's do this one. This is about electric fields. Even though it's not complete, I think we can solve it. Okay. So I'm gonna guess that you have two parallel plates. I think this is a continuation of the capacitor problem, right?
Yeah.
Okay. Let's see. Where's the capacitor again? Here.
I think there's quite a few of the capacitor. I
Yeah.
named them 1, 2, 3, and
All right.
4.
So in this case, the capacitor problem's not actually about capacitors because of that continuation there. It's about electric field. So I think we can put this in. Yeah. All right. Let's do this quick now. So where is it? Capacitor. There's a part 3 to it. Okay. See that. Okay. So there's the first part. Okay, so in this case, because we are not really going to deal with capacitors anymore, we'll just consider this as two parallel plates instead. Okay. The reason for that is most capacitors are actually constructed that way. They're just two parallel plates. Okay. So
Okay.
let's go to the problem. The container is evacuated so that there's no air between the plates, and then they're initially uncharged. Then the power supply is turned on. Draw on the diagram the arrangement of electric field lines between the plates. which one is positive, which one is negative. So going back to this diagram, this is the power supply, so we know which one is positive. This is going to be the positive side of the power supply, right? This is going to be negative. Okay, so that means what happens here, the current is flowing in this way, or you can think of it as the electrons are moving which way? The electrons are moving that way, right? Also the electrons are moving that way. So that means but because of this gap, the electrons can't actually push through like that, right? So because of that, the electrons initially they start moving, they actually accumulate here. They cannot jump over the gap, so they stay there. So that's the right side of the plate is negatively charged. Similarly, all these electrons on this side, they go away through the battery, then into the other side. So the plate on the right, or rather the plate on the left, is gonna be positively charged, like that. Okay.
Okay.
All right. The second part we will skip because that's a capacitor problem. We'll skip that. Okay. Also, we'll skip part 3. Part 3 is also a capacitor problem, not necessarily a parallel plate problem. So we'll skip 3 for now. Okay. All right. So let's go to part B. The graph shows the variation with time of the fraction of the total charges on the plate after the power supply is turned on. So it's something like this. So as you charge the capacitor, this is how it looks like. Okay. Um, and then the container is now open to the atmosphere so that there is air between the plates. This air is observed to conduct and discharge the capacitor when the voltage or potential difference exceeds 9 kilovolts. Assume that the capacitance is of the capacitor. Assume that the capacitor is uncharged when air unchanged. Okay, unchanged when the air is present. Calculate the minimum electric field strength between the plates at which the capacitor will discharge. Okay, this one is still parallel plates. We can solve this. Okay. The idea here now is that the electric field, I'll write the word here, electric field strength, okay, is going to be just the voltage over the distance. So our voltage is 9 kilovolts or 9,000 volts, right? The distance between the plates, let's take a look in the diagram from here. It should be given that what the distance between the plates are. It's not. Oh, yes, it is. It's given here, 3.2 millimeters. That's important here. So we'll highlight that. This is important. 3.2 millimeters. Okay. So the distance is 3.2 times 10 to the minus 3. 3.2. Let's just do it in. Let's do this in 9 times 10 to the 3. Right? This is 3.2 times 10 to the minus 3 meters. So that gives us our electric field strength already. Okay. Let's just put that in the calculator. That's gonna be, what's 9 divided by 3.2? That's 2.81. 2 sig fig, so 2.8. Then 3 minus 3 gives us gives us a 6. So 10 to the 6. You can say this in either, you can just keep it in volts per meter, or you can keep the unit, the number rather, 2.8 times 10 to the 6. But you can also say this as newtons. Hold on. Electric field, newtons per kilogram. No, charge per coulomb. Okay. So this is the answer there. Questions?
No, I understand.
All right, great. So just try to again, the capacitor problems we'll skip for now. Okay.
Okay.
Let's hold on. Let's just see if we can answer part 2. There's a part 2 to this. C definitely will not answer because it requires us to know capacitor equations. Okay. So the last part, part 2, the time it takes for the air to become conducting for the first time. Again, we'll skip C for now, but let's do part 2. Okay, let's take a look at the graph. It says here, um, calculate the minimum electric field strength. We need 2.8 times 10 to the 6 volts per meter. Can we find something from the graph in that? No. We need some sort of capacitor equation again here to use this equation or use this value to determine the charge. Okay, and that is a capacitor equation. So we will skip part 2. Okay.
Mhm.
All right. So we'll skip this as well. Capacitor. So that is done. Um, what's next? So it's done. Uh,
There's a question with light
yeah, the light question. Let's do that.
and the part 2.
Mm-hmm. All right. Let me just check. Okay, we're here. Oh, this is a challenge. All right, so you have monochromatic light entering the base of a plastic container, plastic beaker, contains water, then on oil, an oil layer on floating on it, and then of course air on top. So this is correct. Okay, so the student's diagram has one error at position A, right, and one error at position B. So you're given the refractive indices here, right? So the questions are, what are the errors? So I'll just copy this again. But either way, the question for this bit is only what are the errors, right? Um. Okay. Okay, I have to analyze this a bit to be sure because again, no marking scheme, so I can't just say the answer out loud, right? All right. Let me think for a couple of seconds.
Okay.
Okay, this is air. Okay. Okay. Ah. Uh-huh. Uh-huh. And then okay. Um okay. Here's the what's the error in A? This is position A, right? So look at the remember that this is also air. So that's 1.00 here, right? So this part is correct. So remember that for refraction to happen, when you go from smaller to larger n, the angle should decrease, right? So going this way, angle decreases, right? Angle of, I'll just say angle, refractive angle is gonna be less than the incident angle. Incident angle. Okay. So that means, or going the other way around, if you go from a high n to a low n, the incident angle should be bigger, right? So let's just rewrite. Let's just do that here again, but this time around, I'm just gonna just straight up compare what should happen. So here, what should actually happen here from 1.6 to 1.3? Refraction, the refractive angle should be larger, right? So larger r. I'm just gonna say it here that this is smaller r, right? And then from here to here, there should also be a larger r, right? A smaller r rather. And then finally from here to here, this is a larger r. That's what it's supposed to have, supposed to be. But take a look at A. What is wrong here? What's wrong here is that R is smaller than I, right? So that's the mistake in A. The angle of refraction should be bigger. Okay? Angle of refraction should be bigger. Must be larger than angle of incidence. Okay. Um,
When it's going from a thicker medium to
yeah,
a less.
yeah. So from plastic to water in this case. Okay. From larger than angle of incidence. Okay. Now it does say you have to say the reason. Without the reason, um, it won't you won't get the marks, right? Or at least you'll get only one mark here. Incidence. So the second mark here is the reason. This is because Snell's law. If you need to be more specific, you can say Snell's law. Okay, Snell's law. I wouldn't say states. Snell's law. Did will um lead to a larger uh n angle of refraction. Okay, refraction when uh, the angle of incidence is when n okay, let's just say angle of big there will lead to a larger angle of refraction because n of what was the medium here, n of water is less than oh other way the n of plastic. Okay, so you have to state Snell's law and then the relationship between the ends. Okay, now at the water oil interface here, meaning this is wrong. This is gonna be wrong because this is total internal reflection, and total internal reflection only occurs when the refractive medium has a smaller angle of incidence. So that's the reason there. Okay, if it were going from from water to plastic again, then yeah, it could happen. Okay, uh, I'm just gonna write the answer here. Total internal reflection occurs only when n incidence is larger than n of refractive. Okay, but this is not the case in the problem.
And when does it happen that the um
So it's the other way around. So basically, if this were switched over, if it were oil on top, if it were water on top of oil, we can have total internal reflection. Okay.
and for the plastic and water we measure the size of the angle from the normal, but what if it goes like on the right side? Is it a bigger angle or a smaller angle? Like if the angle goes, it's on the left side of the normal, and if it
Oh,
goes on
okay.
the right.
It doesn't really matter if it's left or right. It won't matter. But what matters is those two angles must be on opposite sides of the normal. Opposite sides of the normal. Okay. So
But
what do I mean by that? So in this case, we're coming in from the right, and then when it enters the plastic, the ray is to the left of the normal, right? But if we do it the other way around, exactly like going like that, we're gonna get the exact same behavior, just flipped over, because it's still gonna have that same idea, that this light on the left is incident here, and then when it gets refracted, it's on the other side of the normal. So left or right doesn't matter. Okay.
so it doesn't have anything to do with the density.
Yes, it does, but generally speaking, it does. But there are certain materials wherein they are denser. Specifically, they are denser in terms of mass, but they have a bigger index of refraction. The perfect example is actually here. Oil is less dense than water, but the refractive index of oil is bigger. But generally speaking, yes, density does play a role in the angle of refraction. What's this? the value of n. Okay.
Okay.
So the light problems are done. And guess what? We're left with relativity questions again. The ones we haven't done yet.
Yeah.
All right, so this is what we'll do. I'm going to change our approach to one of the problems. So far, we've only done either the space-time diagrams or the Lorentz transformation, right?
Yeah.
Now, there is a third approach, and it's going to make it a lot easier for some problems. Okay? Which one? Okay, let's go back to the rocket problem. So I'll just copy and paste everything here real quick. But I'm going straight to the final question for this, okay? Because I think we've done the first few problems with this particular set, right? So we've done this before, and I know we've done this problem, right? But we need the information from both of those to answer this last bit. Okay?
Okay.
All right. So here, and let's just put the last problem here beside it, like this. Okay? And again, right on cue, this is the last page on our board. Tomorrow, we'll use another board. Okay?
Okay.
All right. By the way, have I shared this board with you yet?
I think you shared it last lesson.
All right. Okay, good. Okay, so let's using the space-time diagram or otherwise, whether light from L1 or L2 reaches the rocket first, right? So we can do the space-time diagram. Let's do the space-time diagram here first again, right? First of all, so we'll do the grid line thing that we've discussed yesterday, right? So what I'll do is I'll draw this particular grid line here. I'm just gonna follow this line to make it easier. Let's lock this. Okay, so for this line, it's gonna have to go here, right? And then let's do the other line, like so. Okay, yeah, that's gonna work. Okay, so yeah, this is gonna work because now this tells us that L1 is gonna happen here. Okay, again, this is based on the diagram only. This is L1. There we go. Let's do that again. This is L1. Okay, how do you know that L1 is there? Because remember that in what's this, from the rocket's point of view or the rocket's reference frame, L1 and L2 occur at the same time, and that's the grid line for them happening at the same time, right? Okay.
But how do we know if it's like one or the other? Like we have to.
Okay, because okay, let's label the lines first. So this line here is the grid line. This is a horizontal grid line. Okay, horizontal grid line. This line here is a vertical grid line. Now, which grid line will tell us time? It's the horizontal grid line. Just like this, the horizontal grid lines coincide with the y-axis, right? So in this case, so the horizontal grid line on this thing will correspond to same times. Okay, does that make sense?
But I think the horizontal is the one that's closer to the x-axis at the bottom.
But remember, the horizontal grid line corresponds, the vertical grid line rather, will correspond to, so you're talking this one, right? So this grid line here is a vertical grid line. So it's like these ones. So they correspond to so these corresponds to x coordinates, right? So the grid lines coordinates. And this, the horizontal grid lines will be the CT coordinates. Or let's put prime, yeah? X prime and CT prime coordinates. Now remember, when we're looking at the idea, at the problem, or the problem says that the rocket sees the two events L1 and L2 at the same time. So we're gonna look at the same CT coordinates and therefore the same horizontal grid line. Okay?
Okay.
All right. So that's the reason why. So
And it's we know that it's when it intersects the axis that it happens.
that's right. Hold on, did I do that right or did I kind of mix them up? The labels at least. Hold on. The descriptions are correct, but I think I messed up the. Yeah, I messed this up. This is the vertical grid line. But so let's just change the labels here. Yeah. So this is the vertical grid line because that's X, that's Y. So this is the vertical grid line here. This is the horizontal grid line here. Okay. But still, it's gonna be the same thing. Horizontal grid line do CT coordinates, and vertical grid lines do X prime coordinates. Okay. So, all right. So here is where L1 is. The question now is, okay. All right. So now that we know, so now that basically we've determined where L1 is, so that's L1 where it turns on. Let's go to the actual question. The actual question was determine using space-time diagram or otherwise whether light from L1 or L2 reaches the rocket first, right? So let's look at the space-time diagram first. Let's answer that question. According to the rocket, okay, we're not looking at when it turns on first. We're looking at when the light gets to the space or the rocket first, right? So in order for us to do that, remember that we do have the light cones from light, and the light cones are just basically the 45-degree angle cones. So what we'll do is this is 600, and this is we're looking for a 600 here as well. And all I'm gonna do is draw a 45-degree line like this. Whoops. Let's go back to that. 45-degree angle like that. Okay. Now similarly, we can do this as well. So this is I'm just gonna copy that to make it easier. Copy, and let's move that here. Okay, so that is the light cone for those are the what's this? Those are the light cones from the light. Okay, so according to this, let's take a look at our what's this? At our rocket. Okay, where's the rocket here? So according to our rocket, it travels. Okay, which light actually gets to the rocket first? Let's take a look here. So the rocket, let's do the other. I forgot the other one. Hold on. We need to draw this other side of the light cone here. Okay, how do I flip this over? Is it possible? Okay, I'm not gonna flip that over. I'm just gonna draw one. Okay, it's gonna look. What's this? This is more or less at 1,000. So 1,000. Something like this would work. Yeah. Hold on. I'm gonna draw it here. It's gonna be easier. So 1,000 to 1,000 like that. Then let's move that. Okay. So then, all right. Hold on. So this would be the light's path, right? From L1 and L2. Now, if we look at this carefully, which light actually reaches the position? So because in this case, we want to see the light reaching the what's this, reaching the space station, right? So what we're gonna do is we're gonna see which light intersects with the x prime axis first. And you can already see here, if we continue moving this along. Okay, why is it not moving? I'll just do that. All right, that works. Okay, which one intersects the rocket's x prime axis first?
L2.
L2. Okay, we know the answer will be L2 if you already know how relativity works, but this is how you would show it. Okay, and this is the explanation. um okay, so let's put that
But how do
go ahead, sorry.
for L1 we have the thicker line and we have the thinner line that
Mm-hmm.
goes to the left. So how do we know which one to look at? Because if we look at the left line, it intersects
It
sooner.
intersects here, right? This is because if you go this way, well, think about it this way. The rocket is moving this way, right? According to x, not x prime, according to Earth, right? The rocket is moving this way. So it wouldn't make sense that the light would intersect the rocket here because it's already passed. It will intersect it somewhere in front.
Okay.
Okay. Similarly here for this L2, it would go both ways, but remember, we know that the rocket starts off somewhere here, right? Actually, we know that the rocket is gonna start somewhere from Earth, and it's gonna go this way. So really, what's gonna happen is every time you do it, um, all right, sorry, not the Earth, but the space station. So when the rocket's already somewhere here, the position's already somewhere here, then the light has to travel from L1 going this way, not the backward way anymore. In other words, this is the light going backward, this is the light going forward. And the only way
So
that the
for
light
L,
can, yeah, yeah.
mhm.
So the only way that the light can catch up with the rocket is if the light is moving forward.
And for L2 we're looking at the blue line and not the orange line.
Mm-hmm. Right. Actually, we're looking at this orange line as well. This orange line here. Okay. Now, this orange line here is telling us that the light, there's actually another, I'm gonna do another line for L2 just to let you see what's happening. So L2, this line also exists for L2. Okay. So let's see if I can move that now. There we go, I can move that. Okay. So this line also exists for L2. You see? We always have these two lines that would exist for both light sources. But in this case, the light moving backwards is the one that intersects with the rocket first. Right? Okay. This other one actually won't intersect with the rocket. Not, at least not first. It's gonna... Is it going to actually... I think at this point, it will intersect the rocket some other time. But definitely, it will intersect it here first. So there's gonna be another time somewhere here wherein the light intersects with the rocket, and therefore it sees the light again. Okay.
Okay, so for L we look at the left line, and for
Mm-hmm.
Y or for L1 we look at the right line.
Yes. It depends on the direction of travel of the rocket. If the rocket was traveling backwards, then we would do L2 first, and we're gonna do the one going here, and then for L1 we're gonna do the one going here. Okay, if it were moving backwards. But if the rocket was moving backwards, I'll just draw the line for the rocket moving backwards. Okay, for the rocket moving backwards, it's gonna be like this. These would be the axes. Okay.
Okay.
All right. Okay, so that's using the space-time diagram. Another way, is it possible? Okay, this other one we cannot use the technique using the what was that called? The space-time interval. We cannot use that here yet. Okay, so other problems we will see we can use the space-time interval to help solve. Okay, so hopefully you send over some problems again, or I could look for one later. All right.
I can look for them. So a problem where we have to use a space-time interval to find the location.
Right. Okay.
Okay.
Right. Okay, so yeah, we finished all the problems now. Hooray. All right.
Yay.
Okay, so tomorrow we'll meet again, and hopefully we can do something. Yeah, we can review some more problems here. Yeah. All
Okay.
right. Okay, so I'll see you
Okay.
next. I'll see you next lesson. That's tomorrow. You have a good You have a good day. See you tomorrow.
Okay. Have a good evening. Thank
Bye
you
bye
very
now.
much. Bye bye.
Bye. So here we go. That's the last. That's another lesson down. And this time, Joy, gosh, thank you for joining the stream. I do hope, well, I do hope you found that useful. Not just interesting, but useful. Because remember, we are doing IBDP review here today. Okay, so, um, all right, so we'll end the lesson here today. But before we do, don't forget to like, share, and subscribe to the channel. We are again on YouTube, Facebook, and Twitch when we go live, and on Instagram and TikToks for announcements. I think again, like I said, Instagram's already being consistent with the automatic notifications. So yeah, less work for me, and you still get notified whenever we go live. So with that in mind, I bid you all a good day, or good morning, good day, good afternoon, good evening, good night, wherever you are in the world. Stay freaky, everybody. Bye bye now.